Okay, hello. So I'm back, and let me update the um, this thing. So if you recall, this was my previous little agent seek thing a while ago, and hitting play, you'll see a little orb pops up, and then the humans go and go at it, and then the zombies are trying to get the closest human, and so on and so forth. And they all kind of eventually kind of coagulate in the middle. So I'm going to use this as a base for kind of exploring the arrival, the wander, and the obstacle avoidance stuff that we were talking about in lectures this week. So to start, I'm going to go into my thing here, and I'm going to still create my orb. I'm going to there. I'm still going to create my orb, and then what I want to do is I'm going to create a new game object and human. Great, or no. I'm just going to create a new mhuman, and what I'm going to do then is I'm going to create my little game human object, human game. Actually, let's do this. Mhuman equals game object resources load game object prefab human. This is just loading it from disk because we're not animals. And let's get the get component human, and let's set our ground width, ground height, and right. Let's do this really quickly. Just cut and paste. So I'm going to now let me do it up here actually. Okay. So my mhuman, instantiate my human object, blah blah blah. I'm going to set the ground, set my random position. I'm going to set my seek object, which we'll use very soon in the arrival stuff. And for now, we're not going to avoid any zombies. So let's see what happens here. And we're only going to create now one human object and one orb. All errors Oh, I see. Great. So now you can see my scene has one orb and one human. And the human is ever so slowly going and seeking the orb. Now what also will happen is it will continue to seek the orb as it gets closer and closer. And you can see that it kind of now will oscillate around the orb. So the first thing we want to do is let's add a arrival type of behavior. So let's go to our behave.cs. This may be your vehicle.cs, whatever. And let's go down to our seek, right? Great. And now our seek, we're going to add a little value here, which is going to be called the seek decay. And we're going to define it here. We're going to make seek decay equal to 0. Now if our seek distance is less than, say, 1, and these are all parameters. You can set this stuff, yourself. We're going to make seek decay equal, basically, is going to be equal to 1 to the seek distance. Really, that's all we need. So the closer we are to the object, actually, let's make this 2. Let's make it 3. We're going to make this equal to divided by 3. So the seek decay, when we're at 3 away, is going to be 1. And as we get closer and closer, as the seek distance gets smaller and smaller, our seek decay is also going to get smaller and smaller, which means we're going to reduce the velocity of our agent linearly as it gets closer to. So you can kind of think of the curve as like, okay, we're getting closer now, we're 3 away. Now we're just going to go down with a slope of 1/3 as we get closer to the object. So let's see what happens. So cool. Oh, now we're real far. That's right. We need to make the seek decay equal to 1, not to 0. Otherwise, we won't move. Cool, we're getting closer and closer and closer. Now you can see it'll slow down. Still oscillating. So, what we need to do is not do it this way. What we can do, well, another thing we can do here is it might not be strong enough. So our velocity is only being incremented. Well, okay, actually this makes sense because we're no longer adding to the velocity with the seek. So that's not actually what we want. We don't want it to just do that. We actually want it to slow down. We want to go the opposite direction as we get closer because our velocity is, we don't have any other form of deceleration. So it's like we're on ice. So we have two options. We either add some kind of deceleration force, which we don't currently have in this. So how about we just add that? Let's create a velocity decay or a drag force as well. So one thing we want to do is, let's call this vector 3 v drag is going to be equal to negative 1.0 times the v velocity. Right. Are we maintaining our velocity here? No. We probably have to do this as well. Oh, no. No, v velocity is being maintained each frame. Never mind. So we want to make a v drag, v velocity times some kind of drag coefficient. Let's call it 9.5. So we're going to be reducing. Let's do it like half. It's a pretty aggressive drag that we're going to be applying to our object. And then we're going to v velocity minus or plus equal to the v drag because it's already negative. So we're applying a velocity vector opposite to our velocity. So now there should be a drag that should slow us down. So with a lesser velocity, we should actually slow down. Now, unfortunately, the drag is making us go really slowly. But hopefully you'll notice as we get closer, our human starts to slow down. It's a little bit too slow. So our drag's a little bit too strong in this case, but you can kind of see as it gets closer and closer, it'll eventually stop. So we no longer are oscillating about our object infinitely. The drag's a little bit intense, so let's reduce it down to something more nominal, and we can see now the arrival. And let me maybe make the max speed a little bit higher, because our max speed is getting kind of annoying. Great, and you can kind of see now with a lesser drag, we're still going to overshoot it, but well, actually no. There you go. Nice and cozy with the Orb of Enlightenment. Great. So that's the arrival force. The arrival stuff. The arrival stuff is pretty straightforward. Now let's do a little bit of wander. So wandering, like we're talking about, basically takes creates a force that sort of deflects you a little bit from the direction that you're trying to go. So how about we create a little, and again, I know I'm not doing this with forces and masses like you should be doing in your assignments, but my goal is to kind of demonstrate these things to you, and this should all be done with forces and masses when you actually do your projects. So to create the wander force, right, what we would want to do is we want to create an acceleration in kind of this random direction. So let's just kind of play with that here and create a vector 3 v wander vector. And that's going to be in the direction of our velocity normalized. Oops. And now we have this is effectively our forward direction. So this we don't have a forward. I haven't implemented a direction vector for the objects in this. This is just for demonstration purposes. So right now we're going to use our velocity as a proxy for our forward direction. And what we're going to do now is we're going to then apply, well actually we kind of need a forward direct, it's okay. So now what we're gonna do is we're going to take our position, which we're gonna get from our transform position, and we're going to create kind of a new like wander position. So vector 3 point wander is going to be equal to our transform position plus our, let's call it a float wander distance, which will make it for now 2. And we're going to add to that wander distance times v wander for now. Although we can technically do this, which might be a little bit better for the time being. And let me kill that. And now that's the point wander, but we also need to add kind of a randomized unit vector on the circle, on the unit circle. So vector 3 v random unit circle. Now Unity has a built-in function for this. I'm going to quickly look that up because I forgot what it is. Okay, cool. So Unity has the random dot inside unit. Well, I'm going to use circle because I don't want I don't want to go up and down, but you have sphere as well as circle. I'm actually going to use the on unit sphere. Yeah, I'll do the on unit sphere. I guess I don't have the thing. Great. And then what I'm going to do is to make sure that I only have the x and z, I don't want the y, I'm going to go v random unit circle dot y is equal to 0, and then v random unit circle normalize. And that's what that's going to do, is it's going to kind of give me a random point and then squish it down. And so now what I'm going to do is I'm going to take the v random unit circle and I'm going to add it to my point wander. And then my v wander is going to be the point wander minus my position, and then I'm also going to normalize that. So now I've got a unit vector kind of pointing in a particular direction. And now to apply the wander vector, I simply add that v wander times my wander intensity, which I'm going to set that up as a parameter here, wander intensity, which is going to be, for now, let's do it at 1 and see what we get. And so what we want to see is we want to see a little bit of wiggle in our path, which we won't be able to see. Oh, right. So there's something I forgot to kind of compensate for. Behave applies to the orb as well in this case. And so you can see my orb kind of wandering about randomly, which is kind of fun, so I'm going to leave it for now. But you can kind of see how wander is affecting the orb, and it's kind of moving around a little bit randomly. Let's see what happens when we make that distance even more. So let's say we apply a distance of 10. You'll start to notice that the wandering becomes a little bit more straight. When you make the wander distance 1, it's going to become more random. And you're going to see a lot more movement in of itself. You can even make the wander distance 0, right? And what will happen is you're going to kind of wander about yourself. There won't be forward motion at all. It'll be completely random. As you can see here in the sphere is mostly sticking around itself and kind of wiggling. And in the case of the human, in this case, there's a lot of like movement. It's sort of like, you know, kind of jittery. When you make the intensity really intense, you'll notice that the wander force is really aggressive to the point where you barely get any motion in the direction you want at all. And notice that it can be a bit bad if you make it very slight. You get kind of a more gradual motion. So yeah, fun. So for now, let's make the wander intensity 1 and the distance at 2, which seems to be relatively nominal. Okay, so now we've got these really great little things. And let's implement some obstacle avoidance. So right now we have a random thing, and what we need is we need a new object that we want to avoid. Let's call that a, let's create a new prefab. Oops. Let's create, let's make a big cube or whatever. 0, 0, 0. And this will be our pillar. Let's make this a prefab. And let's to create that, let's scale it up in Y10, and then let's make it a bit bigger. Let's also apply to it a new material. Let's call it, let's make it brown. And in our prefab, let's, I love how that works. Let's put that here. Let's kill this prefab, delete, pillar, and also let's make that position Y5. So now we can, great. Cool. All right, now you've got a bunch of pillars. Well, we have a pillar object. Now we can go into our behave, or our manager, and we can create some pillars. Cool. And let's create a bunch of pillars for us to avoid. So this is going to be our pillar game object. This is called pillar. Pillar game object. Pillar. Which we don't quite. Yeah, let's do that. We need to create a new script here. Oops. Let's call it pillar. No, we don't want that. There we go. And in the same way, right, we want to have pillar extend behave, and we don't want to override the update. What else? And we want to have this for now. Great. Although we do probably want, we don't want our pillar to bounce around, but let's see what happens. Oh, no. Let's go into manager, and then temp pillar, instantiate pillar object. Let's make 10 pillars and pillars add temp pillar. Cool. So now we should probably have a bunch of wiggling pillars. Oh, no, something went wrong. Ah, right. The other thing we need to do is we need to add a script to this. and then save it as a prefab. And now, if we remove it, it should work because we didn't have that. So cool, now all our pillars are moving, which is not at all what we want, but it's kind of hilarious. Great. So to avoid the pillars from moving, what we want is we want to override the update function. And now the pillar won't move. But we do need to set its position. Otherwise it won't update it based on the position we set. Great. But now you can see there's not enough pillars for this to actually work well, so let's increment the pillars to say 50. There's a small chance they might collide, but it's okay. Now let's do the same thing. I'm sick of that orb running around, so let's make the orb stop going crazy. Cool. So right here, like, there's still not a sufficiently high likelihood that the pillars are going to crash into each other. So what we need to do is we need to not random position, but let's do a grid position of I and j. And where is j going to come from? We're going to create a nested for loop here for int j equals 0, j is less than non-pillars j plus plus, and so this is going to give us 10 pillars, grid position. What we can do is we can kind of follow the thing here, public void, grid position in I and j. Float x is going to be equal to float m ground width. I guess we do need to have the number of spacing. Ground width divided by float num spacing times I and then y is going to have the same thing for height j, and there you go. Rand x, rand y, or well, x, y. And height divided by 2, and in this case our pillar is going to have a height of 10. I'm not going to float it. Great. And that should hopefully put us in a grid position. We're going to have some problems here because I need to provide num pillars. Oops. And with a bit of luck, we are going to get them, but it's probably going to be off because I didn't take into consideration the negative. Yeah, there we go. That's not what we wanted. So what we need to do, behave, is go to and then x minus equal floats on ground width divided by 2.0. Right. You can consolidate that into one line, but whatever. No. This stuff always drives me crazy. I don't know how many different ways I've solved this particular thing of getting like a bunch of objects to like align around the center, but whatever. There we go. So now there's a very high likelihood that our object is going to run into any one of these pillars because of the grid pattern that we placed there, right? There's always going to be something in its way. Not sure why the... Oh, because the wander effect is on. Let me turn off wander for behave. For now, while we do the obstacle avoidance bit of the equation. Because that's just going to be really confusing. But cool, it's fun. Like, look, we can see our little cube going at our sphere. And gets it, like a champ. Our cube's a champ. Unfortunately, it's walking through walls to make this possible. So what we need now is we need to add obstacles for it to avoid. The first step is in the same way that we have these seek objects and flee objects, we need to have obstacle objects. Right? And now we need to create an add obstacle object. And, you know, it's all pretty standard fare. And then we go into the manager. And in here, right, in the same way that we were going to do this for the zombies, what we want is for each game pillar object in M pillars, we're going to take our human and we're going to add obstacle object. And that's going to be our pillar object. Great. And so now in the behave, we have a bunch of objects in the obstacle objects vector that we can now use to avoid. Now I'm not going to do this in a separate function like you're supposed to, but that's on me. So the first thing we're going to do, we're going to go through these obstacle objects. Let's do this. So now we're going to do avoid obstacles. And first off, we want to create a list of game objects that are valid obstacles. And so we're going to, for each, game object, obstacle in obstacle objects, if, now this is kind of the fun part, right? If, let's do it this way, vector3 point obstacle object is going to be equal to the obstacle transform dot position. Well, actually, whatever. We're going to, let's do this with v to object. Let's call it v to c, just like it was in the thing, is going to be minus our transform dot position. Whoops. Now we have this this normalized velocity, which is going to represent our direction that we're going, and we're going to do a dot product between those two. So we're going to go v normalized I mean, I could do the equation, but you probably want to use the built-in functions. One moment. Okay, so I'll do it both ways. So this is the way vector 3 dot. That's the way you would do a dot product. So we do the dot product between, this is our velocity, this is our forward direction, and the v to c. I'll do it this way. Alternatively, right, if you wanted to do it manually, the way you would do it would be v velocity dot normalized dot x times v c times x plus v velocity normalized dot y times v2c dot y. And that would be the exact same thing as the above. But I'll go with this for now. And now I'm going to say, if this is greater than 0, then valid obstacles add obstacle. So what we're doing here is we're going through each object and we're saying, is this valid? And if it is, then we're adding it. Right now, what that's doing is it's adding pretty much everything, but only the things that are in front of us. But we don't want to look at everything in front of us. We only want to look at the objects that are in front of us, and we have a likelihood of hitting, right? So here's another kind of trick. Well, we can do the field of view, but really what we want to do is we want to do that projection onto our normal. Now, I'm going to use a bit of we don't want to add everything. I'm going to use a bit of a hack because in the lecture, it's not a hack actually at all, it's mathematically correct, but in the lectures we talked about in 2D. In 2D, to get a right vector, you would have to rotate your vector, you would have to flip the 2 and make one negative. We're not going to do that here because we have a much better approach. We're going to figure out our vector v right is going to be equal to vector 3 cross our v velocity normalized and vector 3 up. And what is up? Oops, no, don't do it. Abort, abort. Anyways, up is basically the j vector, right? I'm sure maybe they even have the j vector, but we could also do 0, 1, 0. It doesn't really matter. So, but the up vector, the vector about 3 has an up vector, has left, right, all that great stuff. It's just a little bit confusing sometimes because your up vector is specific to your object. So if you rotate your object, your up vector no longer is the same, is not 1 anymore. But in this case, because we're always going to be guaranteed to be on this plane, if I take the velocity and I have my up vector, my cross of that will be my right vector. So my v right. And now I can take the vector 3 dot product of v to c and v right. And that's going to, let's call that float overlap. And now, this is actually back to the kind of, boundary thing that we were talking about, where what we want is if overlap is less than the sum of the radiuses of me and the other object. So to get that, right, we want our bounding volume and the other object's bounding volume, which I won't lie, I forget off the top of my head. So 1 second. I'm just not gonna deal with the bounds. My object is guaranteed to have a particular size. My human is going to have, my behave actually defines these things. Where I can say protected float and width, or m side I should say, is going to be equal to 1. And in this case, the pillar m side is going to be equal to 2. And what I can do here is I can do a public float get radius, and that's simply going to return the square root of m width, no, not m ground width, oh, m side times m side, which will give me the diagonal, right? I'm basically, that's my radius in this case. Actually, I want to do it divided by 2. Not the best way to do this, by the way. You kind of want to probably save this as a variable, because like this calculating every frame, so this is not optimal. But just for the time being, we'll do that. And so then I can, you know, basically do, is it less than get radius plus the obstacle, let's go back here because I want to get the this guy. Then we will add it. And so now what we're doing is we're taking the object, we are projecting the object in front of us down onto our plane, right? If that is going to be less than the radius, our radius, our half width, plus the half width of that object. If that's less than, if the overlap is less than that, then it's in our way. And then we add it to the obstacle selection. And let's see what happens. Let me see how often this will happen. So let's attach to Unity. And let's hit play. Bam, so we've got, it's happening a few times, looks like. Great. Now, yeah, great. So now we've got it happening. Now, once we have all the obstacles, let's create a, let me turn this off. 1 second, let me quickly oh yeah, okay. So now what we want to do is we want to apply a steer force away from the object. Let's call it the closest one because we have a grid thing, and there's a lot of different ways to deal with this, but let's find the closest one. In fact, we don't really need valid obstacles in this case. We just need closest obstacle, right? Is equal to null in this case. So if closest obstacle equals null, then closest obstacle equals obstacle. Else if else if the closest obstacle is not equal to null, now we need to calculate the distance, right? So the float distance of the closest obstacle to us, distance of like previous closest, is going to be equal to the closest obstacle transform position minus our position, and then we're going to get the magnitude of that, right? And then new closest is going to be just this obstacle, right? And if new closest is less than previous closest, then closest obstacle is equal to new closest. Oops, obstacle. So let's see this happening, right? Let's attach to Unity, and let's see how the closest obstacle is only going to be the one that's being added. So let's hit play. And bam. So now our closest obstacle is null. We set it. Great. Next time. Now it's not null. And the previous closest one is 45 away. The new one is 35 away. So now we set it to the new one. Now the previous closest one was 35 away. The newest closest one is 25 away. So now that's going to win. Now the previous closest was 25. The new closest one is 25.5. So this must be equally far. So, oh, sorry, the new closest is 15. We didn't update the value. So the new closest one is 15, and then that wins. Now the new closest one is 7. The previous one was 15. Now that wins. And so on and so forth. Now this one next, the new closest one is 47, so that gets skipped. And the new closest one is 38, and that gets skipped. So basically we can kind of see, I wonder if it'll ever happen again. Doesn't look like it, not for a while at least. So what's nice about this is now, not only do we know which one is the closest, we also can now apply a vector. So if closest obstacle is not null, which is important because not all the objects may have obstacles that they're avoiding, so otherwise it'll crash somewhere, then what we want to do is v-velocity plus equals to, first of all, we want to know which direction, so if we want to go left or right. So let's get that v2c vector again. Oops. And let's get that dot product again for our whether or not it's in front of us or not. Actually, we don't want the dot product of this. We want the dot product of the right, of the right, not the front. So we want, here's our right vector again. And now our dot product is going to be this guy. Great. Let's call this side. And so so now we want to do a vector 3v avoid, and that's going to be equal to v right times avoid intensity, which we'll define, call it up here. Let's do it at 1 for now. And then we're going to multiply. That's that. And then we're going to, if side is less than 0 or is greater than 0, then we want to multiply this by -1. Let me just do this. Oh, I was just complaining about my thing. And then we're going to add that to velocity. So why are we multiplying it by -1? If it's greater than 0, why -1? Well, if it's greater than 0, then we want to go in the opposite direction of the right vector, which is negative. Because right now the v avoid is in the direction of the right vector. And if the v avoid, if the side is negative, it means it's on our left, then we want to go in the direction of right. So we actually don't, if the value is negative, then we don't actually want to change the sign. So that's why this is sort of like inverted. And let's see what happens. Maybe I just wrote a whole bunch of bugs. We'll find out. So I can't quite see, but you can sort of see that it is not actually hitting. Oops, maybe not. Now again, like we talked a little bit about this, the avoid vector is happening like all the time. So you can kind of see the problem here, right? You're not going to always avoid it very well because you have all these conflicting forces in play. In a way, what you want is you want the intensity to be related to the distance. So you don't necessarily want it to be 1. You want it to be related to the distance. So let's take this function here, and this is going to be our distance, which is going to be the closest obstacle's distance, right? And we want it to be the intensity to be 1 over the distance. So as we get closer and closer, the force becomes stronger and stronger. When we're far away, it barely affects us at all. We can, in fact, really increment this, as we've seen in the past, by using the power. And so hopefully what you'll see now is as we get close to something, the force of avoiding the obstacle is going to be pretty significant. So hopefully you'll see that here as we get close to this one. You'll apparently not. Looks like we have just created nothing. Okay, one thing we can do, perhaps, is let's try to debug this a little bit. Let me pause really quickly while I think about something. Okay, so to debug this, what I'm doing is I'm adding a material that we can then set when the pillar in particular is the closest pillar to our object. To do that, what we need to do is we need to go into this script here, and in our materials, let's do that. The material for the pillar is going to be normally this pillar material, and then the orb material will be when it's closest. So hopefully, first of all, let's notice that the materials are getting set correctly. Great. And then the other thing is we're going to set v in the behavior when we are the closest object. We're going to set that color to set closest. So hopefully this will errors set closest is public. Hopefully we'll see the objects change in color. As you can see, the closest one is changing. This one's probably there just because of random initialization. So there might be just an issue with our boundary checking, because we can see that it was going around that pillar, but not exactly the way we would like. Now the side is being set to 2, but is that the case? Is that how big our objects are? And that's the problem with using stuff like this. Our scale is 2 and 2, so that is correct. So maybe there's something else that we're doing wrong. Let's see here. The overlap. Oh, I see. So here's a problem with this distance calculation. The distance is actually not taking into consideration the boundary of the object. So as far as it's concerned, the force should be equal, even if it should be related to based on the point. And so the way we can do that, the way we can deal with this, is we can actually take the distance and we subtract out the radius. And what this will do is this will ensure, this will remove that portion, so it's almost like we're drawing a line to our object and then adding a little bit. And so no matter how we do it, there's always going to be this sort of circle around. And that's going to be our new boundary that's going to then affect this super intense, like 10F thing. Not to mention that we also need to subtract our own radius, so that way we remove that other portion. So the distance is always kind of calculated from the 2 points. And now, hopefully what we'll see is when we get close to an object, like this, whoa, a little bit too intense, I think. Something's going on. But you can see there, it's now I'm not sure why it spazzed out that one time. So there's a couple of issues here that were kind of not. There's something wrong. It really should not be looking at these objects that are sort of behind it or to the side, even if they are closer. And so there might be an issue with our code. So the velocity thing, and then we're crossing it to get the right vector, which is correct. Let's add this here. And then we do the overlap. and then we add our radiuses. Let's see, let's reduce this down, because this is a pretty aggressive thing. So we might be just getting really big numbers, and that may be why. Let's try this again. So here you can see it'll go around. So it looks like there's a vector that is not the direction vector is not correctly being drawn, or is not being seen. So let's visualize this with debug lines, which I think many of you will be also doing. So 1 second. Okay, so first thing we can do is down here, we probably want to visualize our velocity. So let's go debug, draw line. So let's take from our transform position to our transform position plus our v velocity normalized. And we kind of want to do it, let's call it, how do we do green? Color.green, and let's do it for 0.5. So first off, let's make sure that our human is going in the right direction. Okay. Great. So it's working okay. Maybe let's multiply this by 2, just so we can... Okay, cool. And let's slow down our player a little bit. And also, let's take a look from the top. Oops. Great. So let's just really quickly see here. Great. So we are going in the right direction. Okay. Looks good. We also want to change this to isometric, so that way we can see it a little bit cleaner. You can see how these ones that we hit really shouldn't have been selected. So there's something strange going on in the neighborhood. Now the next thing we can do down here is we can draw the right vector. Right? We should, when we expect it to look always right. Let's see. Is there a way for us to do? Okay. And we also want this to be false. And let's make this red. And we'll do this V right. Let's hit play. And it looks correct. As you can see, our right vector looks approximately correct. Let's pause it when it... So yeah, it's always being, you know, sent to the correct position. So nice. Now what we want is perhaps we can sort of figure out what this overlap is between the object that we're looking at. One of the things that we can do is we can also draw a blue line, on the closest obstacle transform. And let's just do new vector 3, 1, 0, 1. This kind of makes sure that we know which object. Well, actually, you know what we're going to do? Let's draw a line from this position to our position. How about that? And I think what that's going to show us is where are we actually looking. And as you can see here, that doesn't look right at all. Because even though that object is in theory closer to us, it's not in our path. So we are not looking correctly. So there's something wrong. And so let's take a look here at our code. In our right vector, we take our v to c, which is our obstacle transform position, minus our position, and then we take that overlap, where we take the dot product against the right vector. And let's kind of see when does this happen? Let's go and hit play. And let's see what our overlap value is. Well, here it's negative. And that may also be a reason. So we don't want to look at negative values. Not to say that negative values are not what's important to us, but we need to take the absolute value. And now, hopefully, with the absolute value being used, we'll only be looking at objects in front of us. And you can see there are literally no objects in front of us in this scenario. And that's why there's no lines. Although that should have triggered. Let's do this again. Great, so maybe we can increase this a little bit. Let's put this to 1.5. Not sure why it wasn't. Great. As you can see, it's keeping away because that sphere is right in there. So right now it's going to avoid this one. It still hits a little bit, and that's kind of the annoying thing. Maybe we want to make it not perfect. We want to increase that sort of keep out a little bit more. To increase the keep out, let's maybe add a little 1 point, like a 10% buffer around these. And now, hopefully, it won't crash. And you have to keep in mind, right, that this is always dealing in it's dealing in forces. So you may have competing forces that are pushing you into objects, but if you have a physics engine, it'll hopefully keep you out of them. Great. Cool. What happens if we increase the density of these objects? How bad is it going to be? So you can kind of see now, even with significantly more, we still can get to our intended objective relatively well. What if we go up even further? As you can see, it still tends to work, but you're going to have a bit harder time getting there. So this is pretty cool. Like you can run it. Oh, guess it found it too quickly. So yeah, so that's about it. I mean, you can get more sophisticated with these things. There are better algorithms than just avoiding obstacles, but you can imagine in a scenario where, like, let's go back to our game before. Let's do this, where we have, let's do 10 pillars. We're gonna add, instead of having it here, right? Let's add our zombies back in. Oh. Let's add our zombies back in, and we and our humans. And not only do we want to, add the flea objects for the zombies, we also want to add all of the pillar objects for the humans, and also, and also for the zombies. And let's see what happens. And we probably want to get rid of these debug lines because they will become overwhelming otherwise. And who knows, maybe it'll all crash. But now you can see objects, and they're doing their best. They're avoiding, pillars. They're avoiding each other. Gets a little bit messy. You can kind of see here where a human has basically been pinned, and all these zombies have come in and completely. In fact, it's happened a couple of places, which is sort of what you want to see, right? Where a few objects will basically get stuck where they are because of all the forces are kind of putting them into a this kind of local sort of scenario. And that's happened here too. Everybody's gone and basically have been pinned down. Let's reduce the number of zombies. I think that might. Let's reduce the number of everything. I think that might help kind of make this a bit more sense. Great. So now let's take a look here. And if we hit play, it's a little bit better. You can see objects, then they're all kind of avoiding, like right here you can see they're avoiding the pillars, they're avoiding each other, they're seeking each other. There's some glitch here and there. I think that this is not a perfect solution, but cool. Well, that's yeah, that's it. That's you can see how you can combine a lot of different behaviors and things and create a pretty dynamic, you know, set of things out of effectively very emergent behaviors from a very simple set of rules. Thanks for watching.